Vehicle-to-Grid, or V2G, allows electric vehicles not only to charge from the grid, but also to send energy back to it. This turns EVs into mobile battery units that help support overall grid demand. In simple terms, an EV works like a large rechargeable battery, and grid flexibility refers to the grid's ability to balance power by using resources like these vehicles. For example, some U.S. school districts use electric buses to feed power back during peak hours and recharge at night. As clean energy and EV adoption grow, V2G is becoming essential for improving grid stability and efficiency. So, what is vehicle-to-grid technology? This is a system that allows electric vehicles to both charge from the grid and send stored energy back to it. With two-way communication, EVs can charge when electricity is cheap and discharge when demand is high. Early V2G programs often start with demand response, where the vehicle simply slows or pauses charging during peak hours. More advanced setups let EVs export power to support grid stability and emergency needs. V2G is part of the V2X family, which also includes vehicle-to-home V2H, powering a home during outages or high-cost periods; vehicle-to-building V2B, supporting larger buildings like schools or offices; vehicle-to-load V2L, running tools or appliances directly from the vehicle. Unlike these local applications, V2G interacts directly with the utility grid. When many EVs participate, they can significantly improve grid reliability and help integrate renewable energy. To make V2G work, several key components have to operate together. First is bidirectional power hardware, either built into the vehicle or built into the charging unit, typically cost $3,000 to $5,000 or more. Next are the communication protocols that allow the EV, charger, and grid to talk to each other. ISO 15118-20 for full bidirectional control and secure plug-and charge, SAE J3072 for safe AC V2G with onboard inverters, SAE J1772 as the common AC connector that supports V2G when paired with these standards. Grid interaction. Aggregators like Nuvi or Fermata Energy use OpenADR to manage groups of EVs and respond to utility signals. Utility interconnection approval and metering, required to legally and safely export power. Energy management software, determines when to charge or discharge based on grid needs and battery conditions. When an EV plugs into a V2G-enabled charger, the system follows a coordinated process. 1. Connection and communication. The EV connects to a bidirectional charger and exchanges data through standards like ISO 15118. This lets the system read battery state of charge, availability, and operating limits. 2. Bidirectional power flow. Charging. AC from the grid is converted to DC for the battery. Discharging. When the grid needs support, or during an outage, the charger sends power back as AC. In some cases, the system may simply slow or pause charging to reduce grid load without exporting energy. 3. Grid services. The EV can assist with peak reduction, frequency regulation, and renewable balancing while maintaining required charge levels. 4. Control and safety. Energy management software and the vehicle's battery management system control timing, power levels, and grid standard compliance to protect both the system and the battery. V2G can operate in two main architectures, AC V2G and DC V2G. AC V2G has the inverter inside the vehicle. The EVSE handles communication, while the onboard charger converts AC to DC for charging and DC to AC for grid export. This is simpler, but requires the vehicle's onboard inverter to comply with grid interconnection and safety standards. DC V2G puts the inverter in the charger. The EV connects via CHAdeMO or CCS, and the charger manages power conversion and grid sync. This allows higher power and multi-vehicle support, but needs certified chargers. Bidirectional chargers usually cost from $3,000 to over $5,000. Today, most US systems focus on V2H backup at home, while full V2G at public DC fast charging stations is still limited to a small number of pre-production deployments and compatible vehicles. As of 2025, fully certified V2G is currently limited to CHAdeMO, or Charge to Move, the long-standing DC fast charging standard that reliably supports two-way power flow. Vehicles using CHAdeMO include the Nissan Leaf and Mitsubishi PHEVs. CHAdeMO is gradually being phased out in the US and Europe. CCS, or Combined Charging System, is now the dominant fast charging standard in North America and Europe. It supports bidirectional power via ISO 15118-20, though full V2G is still emerging. CCS-equipped vehicles include the Ford F-150 Lightning, Volkswagen ID.4, GM Ultium Trucks platform, and more. Like any emerging energy technology, V2G brings both notable benefits and practical challenges. Starting with the advantages, it improves grid stability, balances peak loads, integrates renewables, provides backup power, and maximizes idle fleet use. Challenges include limited EVs with bidirectional power, costly chargers, evolving AC V2G standards, such as ISO 15118-20, interoperability issues, battery warranty limits, range concerns, and cybersecurity risks. Still, V2G presents strong opportunities in the future. Fleets like school buses or delivery vans can provide flexible capacity, and advances in battery durability, declining charger costs, standards like ISO 15118-20, SAE J3072, and utility programs are accelerating adoption. EVs are poised to play a key role in grid services and revenue generation. Vehicle-to-grid, or V2G technology, lets EVs act as flexible energy assets, supporting renewables, improving grid reliability, and creating value for drivers and fleets. Still in its early stages, V2G has the potential to reshape how we power our cars and homes, reducing emissions and enhancing energy stability. By 2030, 30 to 50 million V2G-capable EVs are expected worldwide, forming a massive distributed energy resource and reshaping how we power our cars and homes. Thanks for watching, and for more information, visit pro.repairsolutions.com.